All right, so right off the bat, let's define what it means to be absolutely convergent. So our definition: a series is called absolutely convergent if the series of absolute values is convergent. So again, a series is called absolutely convergent if the series of absolute values is convergent. And what we mean by the series of absolute values, this would be like the series from n equals 1 to infinity, where each term of the series, we take the absolute values. So every single term in this series is positive. And again, what we're starting to think about is what happens if series have a variety or assortment of positive terms and negative terms. So we're trying to come up with ways to determine how to handle these assortments of positive and negative terms. One way to think about this is that the reason we care about a series and absolute values converging, so something like what I'm circling in red, is that if this series in absolute values, so again, every single term of the series now is positive, so we're only adding together strictly positive things. If we're only adding together strictly positive things, this series is as large as it can get. Okay? Because we're only adding together strictly positive things. Now, if we think about the original series, we don't take the absolute values of every term, we don't know what these terms look like. So even if we write them down like A1 plus A2 plus A3, or we know what the terms look like, but they could have a weird assortment of, say the first term is negative, the second term is positive, the third term is positive, the fourth term is negative. And we have sort of a weird assortment of positive and negative terms going through this series. So we have a positive term, followed by, say, a negative term, followed by another positive term, followed by 2 negative terms, maybe followed by 20 positive terms. So there's no real structure in which these terms are positive and negative. So what we're thinking about for a series like the one I just wrote was, well, this series, with those negative terms, we know that this series, it has to be less than that series in absolute values. Just because we're literally taking things away. So the idea of absolute convergence, by tossing on these absolute values around every term, like we did up here, is that this series on the right, this is as large as that series can get. We're only adding strictly positive things together, whereas the series on the left here, since we do have some negative signs, that series is going to be a bit smaller. So again, we're kind of thinking of this almost as though it's like a comparison test, but not quite exactly yet. If the series on the right is always greater, and it converges, well, if we take things out of that series, we think the series on the left-hand side should then also converge. In other words, if a series is absolutely convergent, we're going to be able to sprinkle in as many negative signs into that series as we want, and it's still going to converge. Let's do an example. So this example is just asking us to determine if the series from n equals 1 to infinity of, say, minus 1 to the n plus 1 of 1 over n squared is absolutely convergent. Okay. So the first thing that we know is, well, we want to test this series for absolute convergence. The first thing we do, throw absolute values on it. In other words, throw absolute values on each term. So we have our series n equals 1 to infinity. We're going to throw absolute values on this series of negative 1 to the n plus 1 times 1 over n squared. And when we throw absolute values on this series, the series we need to test to see if the series is actually absolutely convergent is the series of just 1 over n squared. Since the absolute values will squash this minus 1 to the n plus 1, so we're going to be left with only positive terms. So the second thing is, once we've thrown that series or those absolute values on that series, we ask ourselves, does the resulting series converge? Because if this series with only positive terms converges, then the series is automatically absolutely convergent. So what do we know about this series? Well, this is a P series with P equals 2. And since that is greater than 1, we get to say that that P series is convergent. However, we can stronger say that this series, because the series with absolute values converges, this series is absolutely convergent. Again, we can say that because we took the absolute values of our starting series and showed that that series with absolute values converges. So therefore, it is absolutely convergent. So, the way that I like to think about this, if we were to write out the first couple terms of, say, the series of 1 over n squared. Okay? So that's like 1 plus 1/4 plus 1/9 plus 1 over 16 plus 1 over 25th plus 1 over 32nd, or sorry, 1 over 36, and so on. Now, we know that this series converges. I'm going to erase this left-hand side for a moment, basically just to say we're only going to concern ourselves with this infinite sum that we know converges. And well, since we know that original series is absolutely convergent, we could come through and say, you know what? I'm going to make the second and third terms negative. And because that original series is absolutely convergent, we're guaranteed that is still a convergent series. Similarly, I could throw another term in the mix. Say I make the sixth term in the series negative. Well, this series is absolutely convergent, or this series is convergent, because the series it's coming from is absolutely convergent, and we can sprinkle in as many negative signs as we'd like into this series, and it's still going to converge. Let's do another example. So this example that we're going to do is going to feel very similar, except there's going to be one slight change. Instead of considering the series from n equals 1 to infinity of negative 1 to the n plus 1 over 1 of 1 over n squared, we're going to concern ourselves with the series now of negative 1 to the n plus 1 times 1 over n. So again, this is now our friend, the alternating harmonic series. And we want to ask ourselves, is the alternating harmonic series absolutely convergent? So the first thing we do, we go ahead, we come across, throw absolute values onto our series. And the series that comes away from that with the absolute values is the series we're going to test for convergence, which will tell us about absolute convergence. And in this case, similarly, when we take the absolute values, we get rid of all those negative 1 to the n plus 1 terms, so we're just left with our friend, the series n equals 1 to infinity, 1 over n, also known as the harmonic series. So we ask ourselves, hey, does the harmonic series converge? Well, in this case, we know that the harmonic series, this thing diverges. So therefore, the series is not absolutely convergent. So it is not absolutely convergent in this case. Well, the next thing we ask ourselves is number 3 now. Does the series with negative signs converge? As in, does the original series we have converge to include those negative signs? So in this case, the alternating harmonic series, we can use the alternating series test. And just like we saw before, the alternating series test, first we test to see if the terms are decreasing. So we have 1 over the next term, which will be 1 over n plus 1. And we want to make sure that that is less than or equal to the current term in the series, which is 1 over n. And we can compare the denominators directly since they have the same numerator. And this is, of course, satisfied. So again, the series that we're originally asking if it's absolutely convergent, we are now just asking, hey, does that series with the negative signs, does it actually even converge? So we're doing the alternating series test. The second part of the test, we take the limit of the positive stuff, which in this case is just 1 over n, and this limit equals 0. So this satisfies both parts of the alternating series test. So series with those negative signs converges. So at this point, what we have is a series that is not absolutely convergent. Okay. Our series is not absolutely convergent, but we showed that, hey, you know what? With the negative signs, that series actually converges. So there's a special name for these types of series. They're called conditionally convergent. So let's define that right now. So again, a series from n equals 1 to infinity of a sub n is conditionally convergent if it is convergent but not absolutely convergent. Okay. So this definition seems a bit funky. The way that I think about conditional convergence is that a conditionally convergent series, conditional convergence needs negative signs to converge. And more than that, it needs those negative signs in a very particular format to converge. Outside of that particular format, we don't know whether that series could converge with a different assortment of negative signs. So conditionally convergent, you can think of those negative signs in that particular arrangement are necessary for that series to converge. Whereas an absolutely convergent series just says, you know what, any sprinkling of negative signs will also make this series converge. We're now ready to talk about one of my favorite theorems from this part of series convergence and divergence. So this is a theorem, which means this is a statement that is always true. If a series from n equals 1 to infinity of a sub n is absolutely convergent, then it is convergent. So to make sense of this, the way that I like to think about this is if this series a sub n, so I'm just going to draw a little arrow. We think about this series having assortment of negative signs. When we test for absolute convergence, we are throwing absolute values around each term and making that series as large as it can. And basically what the absolute value tells us is, you know what? The absolute convergence, any assortment of negative signs will still result in a convergent series. So, this theorem seems really goofy, admittedly. If a series is absolutely convergent, then is convergent. What that means is, if this series is absolutely convergent, we could sprinkle in any assortment of negative signs we want, and the series will still converge. So it's giving us a big umbrella now of possible convergent series. Just like we did with the series example of 1 over n squared, we started just putting in random negative signs and still saying the series is going to converge because it's absolutely convergent. Next, we're going to do an example of absolute convergence, conditional convergence, or maybe just divergence for a series. Stay tuned.